This is the intro video for AP Calculus BC, section 6.2, and we're going to be looking at exponential growth and decay. So let's, in preparation for this, let's do just a little bit of practicing with separable differential equations. We've done this before. I just thought this would be a good warm-up for us to try here, so let's do this. Feel free to pause the video and try this by yourself, and then watch the video if you want to check your answer. So dy dx is equal to 2x over y. Separate the variables. I think I would just cross multiply. So I'd get y dy is equal to 2x dx. Once I've separated the variables, I'm going to be finding the antiderivatives of both. That would give me 1/2 y squared is equal to x squared plus c. I would then solve for y, so I'd multiply everything through by 2. That would give me y squared equals 2x squared plus, I'm going to make this a C1, I'm going to make this a C2. Little note here that C2 is equal to 2C1, and then my final step would be to square root both sides, so it'd be plus or minus square root of 2x squared plus C2. C2 just being, again, just some other constant. All right, so that's just a little warm-up here. We're going to take a look at specifically now growth and decay models. So some of this is old stuff, old review from pre-calc. Let's remind ourselves what are the exponential growth and decay models. They're all based on this idea right here. I think you probably have seen it like this. A is equal to A0 times e to the kt. You've seen this, well, actually go like financially A equals PE to the RT. This is where you have continuously compounded interest. There's all kinds of different scenarios here, but the basic plot is that the amount is equal to the beginning amount, I should say maybe the final amount is equal to the beginning amount times e to some constant times t. So we're going to talk about where that comes from. It comes from this. So if the rate of change of y, which would be y prime, is proportional to the value of y, that would be k times y. So really all this is saying that the rate of change is proportional to the value of y. It's saying that as the amount of y increases, the rate increases. Or as the amount of y decreases, the rate decreases. So in other words, the rate of change depends on how much is actually there. Okay, so the differential equation would be y prime equals ky, or you could write dy dt is equal to ky. So that differential equation, if solved for its solution, would be y equals ce to the kt. And I want to take a moment here and prove that to you. So check this out. If I've got dy dt equals k times y, my first step in solving this, and by the way, k is a constant. Let's keep that in mind. So the first step in solving this is to get the variables separated. The variables are y and t. I would divide both sides by y, and I would multiply both sides by dt. So dy over y equals k dt. I would then integrate both sides, remembering that k is a constant multiple. I would then get ln, absolute value of y, is equal to kt plus c. All right, my goal then is to solve for y. My goal really is to get to this, but solving for y, kind of my focus here. All right, so I'm going to e both sides. So e to this, e to that. That's going to give me absolute value of y is equal to e to the kt plus c. Okay, so let's keep this in mind. The y stands for the amount of whatever it is we're dealing with. And I don't think an amount could ever be a negative. And so I'm going to evaluate something that's positive. I'm going to do an absolute value of something that's positive. So I'm just going to get y here. And then on the right side, we can see that the right side does look an awful lot like this, but it's not that yet. Here's how we get there. Keep in mind that if you are adding your exponents, you're really multiplying your bases. So we could break this apart to be e to the kt times e to the c, and then e to the c, e being a constant, c being a constant, it's just some other constant. So it would be y equals c, this would be like a c1, this would be a c2, times e to the kt. We'd often just write it as ce to the kt. So of course you can see that that matches with that. So that's just a proof of that. You do want to have those skills. You do want to be able to do that on your own. We'll talk about how you would handle one of these growth and decay model and differential equation type things. Get to class and look at those. One last question here. How do we know that it's growth or decay? Comes down to the K value. If K is positive, then we're looking at growth. If K is negative, we're looking at decay. So something to think about there to finish things up. Okay, so that's it for exponential growth decay. Do a couple of examples when you get to class. See you then.